All right, to finish off, we're just going to look just really briefly at some parts of the STLC prop chapter. I don't expect you to look at this in detail. It's just more for just high-level information, unless you really want to go into the detail. But basically what this chapter is doing is sort of setting out the sort of meta-level properties that the simply type lambda calculus, semantics and type system and so on that we did in the STLC chapter, setting out the properties that those things have. So these are related to the strong progress and things like that that we looked for in the small step chapter, but sort of extended more to the typed situation. And again, we're not really considering types in this course, so this is just for interest and just to give you a bit of an exposure to some of these issues with typing. Okay, so I'm just going to scan and just look at a couple of these things in a bit of high-level sort of view. So when we did progress before, we really said that when we have a term t, we either have a value, so we can't do anything more, or we have some term t that we can do a step to. Okay, and this holds for the simply type lambda calculus as long as the term is well typed. And that's what this assumption is saying, is that we have to be able to find some type big T given an empty context for the term that we're interested in. So this is the theorem that really is the key aspect to the relationship between the type system and the evaluation process, which is helping us be sure that if we've correctly typed the program, then nothing can go wrong when we do the evaluation. And this is a really important property for programming languages, because you don't really want to say, well, the compiler said the types were all right, but then when I ran it died, okay, or got stuck somewhere in the middle, okay, more importantly. So for this language at least, that can't happen. So it's using the typing judgment here as an assumption, and given that assumption, then the progress works. Okay. Now the proof of this is quite involved, as you might imagine, but not too long. You can have a look if you want to. They've got a couple of things. There's another theorem that we haven't talked about yet, which applies particularly in typed situations, which is called preservation. So basically, preservation refers to if you've got a term that's got a particular type and you take an evaluation step to get to another term, you'd kind of hope that the term that you end up with after the step has the same type as the term that you started with. So if you start out with a bool typed term, you don't end up suddenly with a function type term after you've done an evaluation step. So this is sort of checking that the evaluation terms aren't making any unwanted changes in the typing of the terms as you go along. So it's called type preservation. Okay, so there's a bit of bookkeeping needed to prove this, and there's some stuff about substitution, which I'm not going to get into. As you see, why we're not spending time on this, because there's quite a lot of detail in these proofs, but we're more interested in the results, not in the details of how to do it. So we finally got to the theorem. Right, so this is saying if I can correctly type my term t to be a big T with an empty context, and then I can take a step from t to t prime, then it should be the case that t prime has type big T as well. Okay, so that's quite a useful one. And I think the last one, back to my thing, so progress and preservation. So let's do uniqueness of types quickly. All right, so here's the type soundness thing. Right, so this is the one that's saying that you can, if you have a correctly typed term and you evaluate it in 0 or more steps to something else, then this term is not stuck. And they've actually got a formal definition of stuck here, which says either it's a normal form, in other words, it can't be evaluated anymore, or it's not a value, in which case you would expect it to be able to step some more. Okay, so this is a soundness result, and they don't actually give you the formal definition of this, but uniqueness of types is useful as well, because you'd like, when you try and look at a term and decide what its type is, you don't want to get two possible answers for that. You don't want it to say, well, it could be a Boolean or it could be a function. Okay, that's for this sort of language. That's a type uniqueness property. As an aside, I'll mention that property doesn't always hold in common languages. So, for example, if you have subtyping in, say, an OO language, you can regard a value or a bit of expression or something as having multiple types, because you can sort of go up an inheritance hierarchy depending on what you need, or follow and go to an interface which might be considered to be a type or a trait in Scala or something like that. So types are not necessarily unique or in the presence of subtyping, but they will be in this language. Anyway, so that's all I really want to say about it. I just wanted to give you a bit of a high-level view of some of these properties. So this sort of thing, like proving soundness and uniqueness of types and those sorts of things, is the kind of thing that programming language theorists like to have, because that gives them some assurance that their type system and their evaluation are cooperating in a sensible way before they go and try and do other things with their language. Okay, so I'll stop there for today.